Mba633 instructional video prepared by Professor Amit Tata, School of Management, George Mason University. This is our sixth video segment on simple linear regression, and we'll continue looking at the diagnostics provided by Excel and their company any regression output using Excel. In the previous video clip, we had looked at the t statistics to determine whether the regression was significant or not. So if you recall, the hypothesis that we were testing, the null hypothesis was that the true slope of the line, straight line that's fitted between x and y, is 0. The alternate hypothesis was that the true slope is different from 0, and we would like to hope that the regression output, the sample statistics that we got, the B0 and the B1 in particular, would enable us to reject the null. So the regression is considered significant if the fitted slope, the B1 that we got from the sample, the 58.959, indicates that we can, with a fairly high degree of certainty, reject the null hypothesis that beta 1 is equal to 0. Because if we are unable to reject beta 1 is equal to 0, then that means that there is a possibility that the true slope of the straight line fitted between x and y is actually 0, which means there's no relationship between x and y. So the purpose of all these t-tests is to somehow, we would like to hope that we can confirm that the null hypothesis, namely beta 1 equal to 0, can be rejected. Okay, so we consider the regression significant when the sample statistics for the slope indicates that the null hypothesis of the true slope being 0 can be rejected. We always want to be able to reject that null hypothesis that the true slope it might be 0. Okay, so in this clip we will look at the f-test for determining the significance of a regression. As it so happens, in the case of simple regression, the result that you get from this f-test will be identical to the results that you get from the t-test, meaning you will reach the same conclusion. Whether you use the f-test or the t-test, you would reach the same conclusion as to whether or not the regression is significant. But let's see what the f-test means and how it's interpreted, how it's computed and interpreted, because when we get to multiple regression, you will find that the f-test and the t-test will not tell you the same thing, will not give you the same information. So first of all, how do we come up with the numbers? Then we will get to the interpretation. So you remember what the total sum of squares, what the sum of squares represented, the geometric interpretation. And you may also remember that the mean squared, ms, mean square is always ss divided by degrees of freedom. So I've written it up over here for you. Mean square due to regression, in this case this 8748562231, the mean square due to regression is equal to the sum of squares for the regression divided by degrees of freedom associated with the regression. In this case it's 1. Similarly, mean square error, MSE, is equal to sum of squares for the errors, that's this number, divided by degrees of freedom for error, which is 18. Okay, so that's how we got MSE. So MSR and MSE, and the ratio of these two numbers was what gave us the F ratio. Okay, so let me just compute that once again. It's MSR divided by MSE, and that's what gave us the F ratio. Okay, so how do we interpret this F ratio? What does it actually mean? What are we doing in this F test? We go back to the hypothesis that we had, and the null hypothesis and the alternate. So the null hypothesis, if you recall, was beta 1 equal to 0. The alternate hypothesis is beta 1 not equal to 0. Now, in the original regression, when we started discussing regression, you remember this line that we had hypothesized as the relationship between x and y. We had said y equals beta 0 plus beta 1x plus epsilon. Epsilon was the error term. Why? Because we knew that the straight line wouldn't be a perfect fit, and hence whatever value, the true value of y is given by this beta 0 plus beta 1x, which is the predicted value from the line, plus some error term, because the actual value is going to be away from the fitted line, either above or below by a little bit. Now, one of the assumptions of simple linear regression is that, or linear regression, is that this error term is normally distributed with a mean of 0, meaning that intuitively these lines, they are rather these data points lie sort of evenly spread out on both sides of the line. Now, any normal distribution, in this case the mean is 0, so any normal distribution also has a standard deviation or a variance, sigma squared. Okay, so when we do this F test here in the regression, what we are trying to do, very much like what we did in our ANOVA test, is that we are trying to compute this sigma squared, the variance of this error term, in two different ways. Okay, so so coming back to let me see if I can switch to, okay, very good. So what we are doing in this F test is we are trying to compute the variance of the error term in two different ways. One is without assuming that the null is true, and the other is assuming that the null is true. So we will compute the value of sigma squared, estimate the value of sigma squared in two different ways. As it so happens, MSE, the mean square error, is an estimate of sigma squared without assuming that the null is true, without assuming that beta 1 is true. So if you recall how MSE is computed, you take the difference between the actual value of the price and the predicted value of the price. You take that error term, you square it, you add them up, and you divide by degrees of freedom. So you had to make no assumption that the null was true. Okay, so MSE is an estimate of sigma squared. Sigma squared is the variance of the error terms. Okay, the assumption was that these error terms are normally distributed. So MSE is an estimate of sigma squared without assuming that H0 is true, without assuming that beta 1 is 0. Now it can be shown that MSR is also an independent estimate of sigma squared, assuming that the null is true. Okay, so this should you may recall we did the same sort of mental exercise when we were doing ANOVA, when we were trying to test the equality of means of multiple populations. The way we did it was to compute the variance of these populations in two different ways. One way was without assuming that the null is true. The second way was assuming that the null is true. Okay, so this is the same sort of logic over here. We assume that the null is true and compute what the variance of the error terms might be, and then we don't assume that the null is true and do the same calculations. All right, so this MSR and MSE are two different estimates of the same quantity, sigma squared, the variance of the error terms. Okay, so MSE is the estimate without assuming that H0 is true, and MSR is the estimate of sigma squared assuming that the null is true. All right, so if the null is true, the ratio of these two quantities, MSR divided by MSE, this will be close to 1. Okay, so we would ideally like to see values of F that are much higher than 1. That would lead us to reject the null. Okay, so if this ratio is close to 1, then we would say, well, you know, my null is, I cannot reject the null, and that would be unfortunate, because that would mean that the regression is not significant, meaning that the values of the slope that we got from the sample we are unable to reject the null hypothesis that the true slope might be 0. Okay, so let's see what we got in for this particular problem. MSR divided by MSE in our case ended up being 23.81. So that seems to be vastly different from 1. But how can we quantify how different this ratio is from 1? So you remember how the ratio of two variances to see whether they are very different from 1, whether MSR is very different from MSE. You take the ratio and see whether that ratio is very different from 1. So we got an F ratio of 23.816. Is it very different from 1? How do we compute the probability? We use the F distribution. So this is the F value, 23.816. You know that 23.816 is the ratio of two numbers, MSR and MSE. So there are 2 degrees of freedom. One is for the numerator, which is 1, and the degrees of freedom for the denominator is that for the residuals, which is 18 in this case. So we end up with a probability of 0.0012. So coming back to our null and alternate using the f-test, here is what we conclude. We are concluding that based on what we see in the sample, if I reject the null hypothesis, there is only a 0.00012 probability of my making a type 1 error. Okay, so I very confidently reject the null and say that the regression is statistically significant, meaning the slope that I obtained from the sample of 20 houses enables me to conclude with a fairly high degree of certainty that the regression is significant, meaning the true slope of the line associating square footage with price is indeed different from 0. I will make that call with a very high degree of certainty. And notice that the p-value that I get over here with the f-test is identical to the p-value that I got from the t-test. And this will only be true when you are doing simple linear regression. When you get to multiple regression, these two p-values will be different, and the f-test and the t-test will tell you slightly different things. They're both trying to tell you whether or not the regression is significant, but in a multiple regression you will have more than one independent variable, and the meanings of the diagnostics with the f-test and the t-test will be slightly different. So all taken all together, the r-squared value, the t-test and the f-test all tell you something about the quality of the fitted line. The r-squared tells you how much of the variability of the dependent variable the straight line is able to explain, the fitted line is able to explain. The higher the value of r-squared, the better. The highest that it can go is 1. But the t-statistic and the f-statistic, so the t-test and the f-test are really tests of significance in the sense you want to say whether the line that you have fitted is statistically significant, meaning does the slope that you obtain from the sample, does the coefficient that you got for the slope enable you to reject the null hypothesis with a very high degree of certainty. You'll never be absolutely sure, okay, but can you reject the null hypothesis with a very high degree of certainty? And what is that null hypothesis? The null hypothesis is that the true slope of the fitted true slope of the line connecting square footage with price, connecting the dependent and independent variable, that true slope is 0. That's the null hypothesis, and we are absolutely afraid that we will be unable to reject the null, because if we are unable to reject the null, that means the regression line, even though we have fitted it with a non-zero slope, is pretty useless, because I'm unable to reject the possibility that the true slope is 0. If the true slope is 0, there is no relationship between x and y. So we are always trying very hard to see if the data can convince us with a fairly high degree of certainty that the null can be rejected. The null being that beta 1, the true slope of the line, is 0. So all regression, whenever somebody does regression, they're praying and hoping that the t-test that they have here and the f-test that they have here will enable them to reject this dreaded null that beta 1 is 0. Because if they're unable to do so, that means the regression is not significant. If they're able to reject this null hypothesis, then and only then is the regression statistically significant, and should they feel confident to go ahead and use the fitted line for making predictions or estimates of the dependent variable.